लास्ट क्लास रे कौन थिला हमरो
जॉइंस पढ़ुଥିଲେ परा लास्ट जॉइंस और टैग विजुअलाइजेशन
ओके जॉइन सॉरी ये थिला बोधे ना नेक्स्ट हमरो होइबो okay today we will run the repartition and coalesce and then the function and performance optimization. ମୋ voice ठीक रे आछे ना
हाँ
okay so before learning repartition and coalesce first we need to understand partitions properly because internally Spark is completely dependent on partitions. Right now we are running Spark like this: create a Spark session, then we pass the master local asterisk, and here the local asterisk means Spark will use all available execution thread from our machine because currently Spark is running in our local machine. So it is use all the available thread from our local machine. So even though we are not using a real cluster right now, Spark still tries to do parallel processing inside our laptop itself. Now let's understand why Spark even created this partition concept. Suppose in real time, we have a data of like 500 GB. of data. Then, so the question is, can one machine process the entire data set together efficiently? And the answer is no, because 500 GB is a huge data, and even if the RAM even if RAM is huge, processing everything using one CPU become very slow. So Spark follows distributed processing. Instead of processing the entire dataset together, Spark divides the data into smaller pieces like this. This is the 500 GB of data. Then it will divide like 128 MB of data. So internally Spark divide like this, means that 500 GB of data, it will divide so many partitions of like 128 MB or whatever we partition size we set. So these smaller pieces are called the partitions. These smaller pieces are called the partitions. Now, suppose let's see an example like this is our data set. Suppose we created the data frame like this, and the columns are ID, name, and department. Now, from our side, it look like one data frame is created, but internally Spark does not think in terms of one complete data frame. Internally, Spark immediately divides data into partitions. Now, if we see the partition count, uh, df dot attribute dot the number of partitions. If we run these,
initially there is 4 partition of what
sorry,
3
कौन कहलो? Hello, किसी पचार लगी?
no initially there is 4 partition of what I'm asking
No. It according to our internal
oh,
thread.
oh.
Means my
Okay,
laptop
okay.
is 20 cores, so it is created 20 partition internal initially.
Okay, as for the course.
Yes. So now this is very important. We only have 10 rows. Here we only have the 10 rows. But Spark created 20 partitions. So Spark does not create partitions based on row count. Spark also consider available execution thread, default parallelism, local execution capability, and in my machine, Spark detected 20 execution slots. That's why it created 20 partitions. So according to, and also it will possible to create 20 tasks in future. With 20 partitions, then it will create 20 possible tasks in future. We'll see that in that future. So now let's see the actual data inside partitions. Means we can see there is 20 partitions, but what inside exactly is partition? First is we can write like df.rdd.glom is a function and then collect. This will show each partition data. See, this is the actual partition data internally Spark created. So format this. See, this is the actual partition data. It created the 20 partition internally. When I create this data frame, we can see like this is a one data frame, but Spark internally create 20 partition like this. There is 20 partition and some of our it contain data and some of are empty. Like partition 0 is contain the empty data and partition 1 is see, internally it will like this is the partition 0, this is partition 0 and this is partition 1. So it's a nitrogen. See, so now this output is very important because now we can literally see which partitions contain data and which partition are empty. Internally, distribution becomes something like partition 0 is this data and partition 1 is this data, like this. Now, so Spark always works on partition by partition and it never full data frame together. Means it process partition by partition, it never process the full data frame together. Now, the next important concept in Spark is one partitions equal to one task. As you see, one partition equal to one task. So this is one of the most important Spark concept. If data frame has 20 partition, then Spark will create 20 tasks internally. Now understand this carefully. Partitions store data. Tasks process partition data. So internally flow becomes like, first it create the partition, then task created, then task processes partition data. The flow become like this. A task is basically the execution unit of Spark, like this. So it internally creates so many partitions like this. So for each partition, it will create one task. Task 1, task 2, task 3. And in this way, it will create 20 tasks for the 20 partitions, because we saw the initially our initial partition count is 20. So in Spark internally create 20 tasks. Now the next question is, who execute these tasks? That is where CPU cores come into picture. Tasks run on CPU cores. So internally flow become again task created, then task assigned to core, then core executes task like this, and this will be the internal flow. Now suppose Spark create 20 tasks and our machine can run 20 execution thread simultaneously, because my machine is 20 core, so it will execute 20 tasks parallelly. Then internal execution become something like task 0, and it will process this partition 1. Then it will create another task 1 which process partition 2, sorry, partition 1. Then it will process the partition 3, and it will process the partition 19. So internally the flow is like this. Core 1 create the tax 1, and it will process the partition 1. Core 2 create the tax 2, and it will process the partition 2, and so on. Now remember, many partitions are empty. See, we can see here many partitions are empty. This one empty, and also this one empty, this one empty. So many partitions are empty. So only partitions containing rows actually do real work. Now this line is very important. Partitions decide task count, and core decide how many tasks run simultaneously. So the actual concept is, partitions decide task count and core decide how many tasks run simultaneously. So this is very important. This is the real internal relationship. Now let's trigger this execution. If we trigger this execution, And as we know, so is the action. So the moment action run, Spark starts execution internally. Now let's understand the Spark UI. Before going to the Spark UI, the moment action run internally, Spark create like when we call a action like this. Suppose we call the action so, and internally the Spark create jobs, then stages, then task.
Yeah.
Internally it will create like this: first job, then stages, then task. This is the actual internal flow, and internally execution flow becomes something like this. The actual flow become data frame, then partition created, then task created, then task assigned to CPU core, then data processed, then present. Internally, this will be the flow. We can see in the DAG. Now let's see in the DAG. This is our DAG. Inside this job tabs, we can see like multiple jobs, something like job 0, job 1, job 2, job 3. Now, usually we get confused here because we think like if data frame has 20 partitions, then why Spark did not create only one job? Because partitions, jobs, stages, tasks are all different things. So partitions decide how data is divided, and tasks decide how partitions are processed, and job decide execution triggered by action, and also stages decide execution boundary inside job. Now we can check Spark UI carefully, like when we saw task count like 20, 1, 4, 15 in this. So this is so much confusing. So now this does not mean Spark is randomly creating new partitions every time. Total data frame partitions are still related to execution plan. Spark is simply processing those partitions across different execution phase internally. Now, in one stage, this stage, this job 01, if you open this is stage 0. And this stage 0 is created the 20 tasks because we have the 20 partitions. So it will create the 20 tasks. And because as we know, one partition equal to one task, so it will create the 20 tasks. And the internally execution becomes something like this task 0 check partition 0, and this task 1 check partition 1, this task 2 check the partition 2, and like this. But only partition containing rows actually process data. It will show all the partitions, but actually which partition contain actual row, that is actually processed data. Now in Spark UI, we can see 4 jobs, and first job, which is job 0, is created due to this job is created due to this line. When we call this line exactly df.rdd.clume.collect, when we call this line, this first job 0 is created. Now let's see inside that what is actually inside this. Now in first step, we can see the parallel collection RDD. This is the starting point. Spark takes our Python list, which is this is basically our Python list. We pass the data as the Python list. Spark internally takes our Python list and converts it into an RDD, parallel collection RDD. In this step, internally Spark did like as I said, this is the starting point, and inside this, Spark takes our Python list and converts it into an RTD. So internally, it is processed like Spark dot Spark context dot parallelize data, and this data is this data, the Python list. It internally take this data and convert it into the RTD in this first step. This is the starting point of the Spark, and it will create that this is because of this it shows the parallelize this part. Because of this it shows the parallelize, and because if we understand internally what happened actually when we pass this data internally, it goes to the driver memory, and Spark splits data into partitions like we saw the before, like this. Internally it creates these partitions when we pass that data, like partition 0 contain this empty data, and partition 1 contain the Rahul ID1, name Rahul, department ID, department is IT, and like this all partition contain the data, and this become the parallel collection RDD. That's why it shows the parallel collection RDD. This is the first step, and now the next step is in this step Python RDD. In this step, Spark prepares Python objects for distributed execution. As we know, Spark core engine is a JVM, but we wrote the code in Python. So Spark must create a bridge. Spark must create a
That Py4j bridge.
yes bridge between Python and JVM, so that it internally process Python code into the JVM. JVM like this. And this node handle Python serialization and deserialization, because this is converted Python into JVM, and where it needed also it converted JVM to Python also. In next step we can see that. Then in step 3, this is the actual serialization and serialization step. Here we can see the ser D. See, here we can see the ser D. Ser D scala. Sed util.scala, and this is meant by serialization or deserialization. In this part, Spark convert Python tuple objects into Spark internal JVM format in this part. That's why it is called the serialization and deserialization part in this part. Now in next part, and we have a question like here, why we see the map partitions RTD? Because Spark process one partitions at a time. Instead of converting row by row, it converts partition by partition, which is more efficiently, and this is the internal process of Spark. Then in step 4, map partitions RDD. In this part, Spark is mapping Python rows into Spark SQL rows. Something like 1 Rahul IT. This will be the internal row. We pass each list like this, and internally Spark will consider each list as a row, SQL rows, because Spark SQL engine cannot work directly with Python tuple, so it needs a internal row. So that's why it converted into the internal row in this part. Then map partitions RDD. This is very important step. This is where schema gets applied. Like we pass the schema like the ID, name, department, like this. We can see here we pass the schema like this. So,
So
and
it will
now,
assign to those.
yes, it will assign this schema to those, because internally Spark decide ID is a long type and name is a string type, and then department is a string type. It will decide automatically internally which column is which data type and assign according to that to the column. If we can print the schema here, df.print schema, we can see the actual data type. See, internally it will assign like automatically detect ID is long type, name is string, department is string, and according to that it will assign ID to this and string sorry, name to this and department to this. This is internally working. And before this step, till now, before this step, this above all the 4 steps is just a tuples. After this step, a real data frame is created, means real data frame row is created. Now, in next step, in this part, actually there is two steps. First of all, this step, whole code gen, whole stage code gen, this part. In this part, this is actually a Spark optimization internally. In this part, Spark generates optimized JVM bytecode dynamically. So instead of row 1 by 1, Spark creates optimized Java code. This is a huge performance optimization, and this is happen internally. So we write like Python code. So internally, it will convert the into JVM bytecode dynamically. Instead of row 1 by 1, Spark created optimization Java code. So this is a huge optimization performance. Then in next step, this part. Now in this part, data is moving back to JVM to Python. And here is question is, first it converted Python to JVM, then why it need to JVM to Python again? because we use this part gloom dot collect, and this part is needs Python object. So again it converted to JVM to Python. Now next part. SQL execution RTD, and this represents Spark SQL execution boundary, and this is where Spark SQL query execution happens. Even though our query is simple, like we use the df.show, this is a simple query, but still Spark create SQL execution internally. So that's why it shows the SQL execution RTD. Then in next step, and this is also another conversion layer. Here Spark convert JVM rows to Python rows for output, because in the end we need the output in the Python code, Python rows. So internally it convert again after the all processing done, it will convert again the JVM rows into Python rows for the output. Then the final step is sorry, not final. Then next step, map partition RTD, and this is the final partition processing before result is sent to driver. After all the processing, it will collect the result and it's sent to the driver. This is the final. Then in next step, this is the final action, because we use the collect. Here we use the collect. So this is the final action, and collect is a actual execution, means actual action. So it, when we call the collect, it trigger the actual execution. Before this part, actually before this part, those all are the inside the lazy execution, because as we know Spark is a lazy execution. So until we call a action, it will just plan those things internally, and when we call the collect, it will execute the actually execution started. Now Spark executes everything and then it shows the result like this. Now if you can see in Spark UI, this is just a job 0, this is our first job, but what is inside these 3 jobs? So now for second job, which is the job 1, this is single line is very important, because see, when we trigger this line df.show, this job 1, job 2, job 3 is started accordingly. First is job 1. If you can see, so when we call the show, Spark does not immediately read full data. Spark is also internally very smart. It first check, can I get enough rows quickly? So for that, it will first create one task. So first it will create the one task and read the one partition file. So like from this, it will check, can I get the enough row? Because as we know, show only shows the, means when we call the show function, it will only shows the top 20 rows, not more than that. So according to that 20 rows, it will first check one partition, then it internally say like, can I get enough rows quickly, and then so that it will create the one task. But Spark found not enough rows yet, so it start another job. Because in partition 1, if you can see here, because in partition 0, this is empty file. So due to this, again it start another job, and in next job it will take 4 partition again and create the 4 tasks. Now here also it will internally says like not enough rows yet, so it start another rows, because to complete the 20 rows till now it will take only this much of partitions, and in this total 5 partition it will only get the 3 rows. So according to that, means it needs 20 rows, so according to that it again start another job, this one, and in this it take the all the partitions. And also internally it say let's read more partitions, and this time means this time it will take the 15 partitions. Now Spark scan 15 partition, so 15 tasks is created. Now Spark finally has enough rows for shows, and then it will stop. Now another important thing is we used local asterisk. So driver, executor, task, and course, all are everything exists inside our own machine, because this is a local machine. But in real time, all the partition is present in different machines. So due to this local 0, it shows the executor ID is driver, because all things are inside one machine. So it is shows the executor ID as driver, meaning no separate worker machine exists and no real distributed cluster exists. Spark is basically simulating distributed execution concept inside our laptop. Because of this, it will show the executor ID as driver. Now let's move to actual production scenario. Means what actual happened in production. Suppose company has 5 worker machine. This is worker 1. This is worker 2. This is worker 3. This is worker 4. And this is worker 5. And each machine has 16 core. Suppose it has like 16 core. Each machine has 16 core. In my laptop, I have 20 cores, so it will create the 20 partition. But in real time, suppose there are 5 worker and each worker has 16 core. Now cluster total become how much? 80 core. It will total create the
It will vary to vary the laptop or what the default will be.
sorry, कौन कौन सा सुबह
The default core will be 16 core or it will vary from laptop to laptop.
See, when we create a cluster according to availability, we pick that means this is not a default means fixed size core. We can also increase the core, also decrease the core. But this is a real-time scenario. Suppose we take like an example. Suppose there are 5 worker and each worker they take 16 core. So total will be the 80 core now. Now
Okay.
suppose in the real time, actually we have a 1000 of partitions in our data frame. There are 1000 of partitions. Suppose in real time. 1000 of partition. So according to Spark rule, if there are 1000 of partition, then Spark create 1000 of task. Task. Now task gets distributed across executor, right? These are all the executor. Now executor 1 means worker 1 has 16 code. So from these 1000 tags, it will process 16 tags at a time. Means like see, from this 1000 tasks, it will process 16 tasks. And this executor also process 16 tasks. This also process 16 tasks. It's a 16 tasks. It's 16 tasks. Internally, actually happen like this. So now total simultaneously, how many tasks is running? 16
80.
80.
into 85 equal to 80 tasks. So this is actually happen in real time. Currently we see our only 20 tasks parallel running because our all those things are inside one local machine. But in real time, there are so many machines, and each machines like is a one laptop. Means if there are 5 machines, that is means by 5 laptop, and the 5 laptop is 16 core and total is 80 core. And if the partition size is 1000, then it will process create the 1000 tags, and each worker is process 16 tags at a time simultaneously because of each worker is 16 core. So now as task finish means after the finish of 80 tasks, then again it will assign another 80 tasks from this 1000 tasks. And in this way, Spark actually internally process the data. Means in real time, there are not basically 5 MB or 10 MB of data. In real time, there are huge of data, like 500 GB, 1 TB of data. So in this flow, actually internally, Spark process the data chunk by chunk. Now, this is become actual distribution computing because now partition exists across multiple machines and executors communicate through network. Remote partition transfer can happen. Because of this, in our case, we can see, if we see this part, till now there is no shuffling, so we cannot see that because in our case it is inside one machine, so there is no network transfer and not remote read write. But in actual real time case, there is 5 different cluster, 5 different machines, so there will be remote partition transfer can happen. In our laptop, everything is processed locally, mean data, task, executor, all inside exist in same machine. So no network transfer required. But in production, partitions may exist across different worker machine. So during joins, group by, repartition, window function, so basically any wide transformation, Spark may move data between executor. And this movement is called the shuffle. This movement is actually called the shuffle. And shuffle is one of the most expensive operation in Spark. Till now, any doubt?
No.
Okay. Now, next we can see the repartition. Now, repartition is the real distributed computing part of Spark. Till now, we saw partition exist, tags exist, executor exist, but data was mostly staying inside its own partition. Now, with repartition, Spark will actually move data, then recreate partitions, then create shuffle, then create new stages, then redistribute rows internally. Due to repartition, this will happen internally in Spark. And this is the one of the most important concept in entire Spark. For this, let's understand by taking an example. Suppose we take step okay, already we have. Suppose we take this data. For this data, we can see like it has initially we saw the 20 partitions because according to our core, it will create the 20 partitions, and each partitions is provided like each task, meaning data. Uh, see this one. This is the actually. Here, the data distribution is poor. Partitions are unbalanced because some partition empty, some partition are contain data like that. So this is the partitions are here the partitions are unbalanced. So internally it becomes something like this, like empty partition. This empty partition is partition 0. This partition Rahul is partition inside partition 1, and then another empty partition. Then Oman is partition inside partition 3, and like this. Now, why this is bad? Because Spark always works partition by partition. As we see, Spark always work partition by partition. And as we know, one partition is create one task. So now Spark must create 20 tasks for this 20 partition, and many tasks will do nothing, process empty partitions, waste CPU resources because there are so many empty partitions, but still they are processed. But due to this, those are waste CPU resources, and this is one reason a repartition becomes important. Now let's run a repartition. Um, Now let's run the repartition. Repart df equal to df dot repartition 5. Suppose we want 5 partition from 20 partition. Now here we think like Spark just changed metadata, but internally if we run this, so here we think like Spark just changed metadata, but the answer is no. And internally Spark will read old partitions because initially we have 20 partitions. So first Spark will read those 20 partitions, then collect rows, then redistribute rows and create new partitions. This is a heavy internal processing. We can see in the DAG later. First, let's check this, how many partitions it will create. See, Now the partition count is 5. So now
So
to
according to data, we can adjust partitions by
yes,
using
according to
repartition.
the data, because see, as we
So
know,
that the extra partition ମାନେ ଖାଲିରେ ଯିବନି ସେ ଯାକ
ହଁ ସେଇଟା
use
ଯୋଉଟା
ହବନି।
ଏମ୍ପ୍ଟି ଥିବ ସେଇଟା ସପୋଜ କିଛି ଦରକାର ହିଁ
ହୁଁ
ନାହିଁ ନା,
ହୁଁ।
କାହିଁକି ନା ଆମେ ଯେତେବେଳେ ପ୍ରୋସେସ ହୁଏ
ସେଟା wastage of resource ହେଉଛି
ସେଇଟା
ଆମର।
ୱେଷ୍ଟେଜ, ସେଥିପାଇଁ ଆମର ରିପାର୍ଟିସନ କରାଯାଏ।
ହୁଁ ହୁଁ
Now
ହୁଁ।
20 old partition become 5 new partitions. Now let's see new partition data actually. As we see previously, let's see. Five partition. No, this is the actual partition. See, when I format this, see, now this is our 5 after repartition. This is the 5 partition 5, and each partition contain so many of data. Now look carefully here. Earlier, Rahul, this Rahul, this Rahul was in another partition, because suppose it is inside partition 1, and also Oman is another partition, was in another partition, and Priya was in another partition. But now Rahul and Suman and Rohit, these all are inside one partition, because initially Rahul, Rohit, Suman all are in different partition. But now after repartition, Rahul, Suman, Rohit, these are inside one partition, and Aman, Kiran as together, John, Vikas are together, and it create one partitions. Meaning SPAR physically moved rows between partitions. When you run repartition, the shuffling is happen, and SPAR move rows internally between the partitions, and this moment is called the shuffling. This moment is called the shuffle. Now this is very important. Why repartition causes shuffle? Because SPAR cannot convert 20 partition to 5 partition without moving rows. SPAR must internally do like read old partitions, then collect records, then redistribute records, then create new partition. This will happen internally when we call a repartition, and that distribution becomes, just a minute. Hello?
Hello.
हाँ uncle. ଓହୋ, ତ ଏବେ କୋଉ ଦିନକୁ କରାହବ କଥା?
ଦେଖିଆ କାଲି
ଓହୋ ହୋ, ହଉ ଠିକ ଅଛି, ମୁଁ କହିଦଉଛି ତାକୁ। ତ ପଚାରିକି କହୁଛି ଯଦି ସେ କହିବ ତାହେଲେ ହଁ ହଁ so when we call a repartition internally these processes happen. These processes happen and that distribution become the shuffle. Now because data movement is happening, repartition becomes a white transformation. See, white transformation. So where data movement is happen, that is a white transformation. So according to the repartition is a white transformation. Now let's understand what transformation. As we can see the narrow transformation. And in narrow transformation, the transformations like select,
Select, filter.
filter, and with column, and so on. These are the narrow transformation. And in these, data does not move between partitions. Internally, it look like from partition 0 to partition 0. And it is like partition 1 to partition 1, then partition 2 to partition 2, and so on. Because it is not dependent on another partition. It's simply partition 0 to partition 0, like internally it is like that. Means one child partition depend on only one parent partition. This is called the narrow dependency. Now let's understand white transformation. White transformation. And the white transformations like repartition, then equify, then join, then order by, and so on. Those are the white transformation. Now, one partition may send data to many other partitions. Something like uh, it will send the old partition 1 to partition 0 or partition 2 or partition 4. Okay, send like this. This is not a fixed. Internally, it will move the partition 1 to send rows the partition old partition 1 to partition 0, partition 2 according to the our operations. Similarly, internally happen like this. Now, dependency become many to many. This is called the wide dependency, and transformation with wide dependency are called the wide transformation. So this is one to one, and this is many to many. So this is the narrow and wide transformation. Now let's see this in DAG actually. When we see in the DAG, see here, it shows the whole stage code gen, then exchange, then again whole stage code gen. And now this middle operator is exchange is extremely important. Whenever SPAC shows exchange, that means data movement is happening now, meaning shuffle started, rows are moving, and partitions are recreating, stage boundary created. So the moment you see exchange, immediately think shuffle is happening here. Now let's see our physical plan internally. You can see our physical plan now. Explain to make on this. It will show actually SPAC physical plan internally.
This physical plan is done by the catalyst optimizer, right?
Yes, it's internally handled by the SPAC.
But RDD, after processing in RDD, it will not undergo in catalyst optimizer, no?
Yes, means after
Only,
converted. Yes, yes.
no, only in PySpark code will go under go under catalyst optimizer or RDD codes also.
No, the
While,
whole code is goes under the means internally
hmm
when we execute all the code, internally
hmm
Catalyst Optimizer read that code and internally it create the physical plan. Like here this. First
if
it
we write that RDD code back then we used to at first that code,
means this part RDD.
no, not this part. The codes which the Bhai at start, the Bhai used to write those codes, parallelized and lambda, something like that. Those RDD codes. Hello.
Yes, ମାନେ ବୁଝିପାରିନି କୋଉ part ତମେ କହିବାକୁ ଚାହୁଁଛ?
ମାନେ ଯୋଉ ଫାଷ୍ଟରେ ଦେଖ ଭାଇ ଯୋଉ ଆରଡିଡି କୋଡ ଯାହା ରାଇଟ୍ କରୁନଥିଲେ ଟିଏଫ ଆମର ଯୋଉ ପାରାଲାଲାଇଜ ତାପରେ ଲାମ୍ଡା ଏବେ ନାଇଁ ପୁରା ଷ୍ଟାର୍ଟିଂ
ଓକେ
ରେ
ଓକେ
ଯୋଉ
ହଁ ହଁ ସେଇ
ଆରଡିଡି
ପୂର୍ବ
ରେ ଯୋଉ
ପ୍ଲାନ୍
କୋଡିଂ
ହଁ
କରୁଥିଲେ ସେଇ
ହୁଁ
ଯାହା
ହୁଁ
କାଟାଲିଷ୍ଟ ଅପ୍ଟିମାଇଜର ରେ ଯିବନି ତ
ନାଇଁ ଏଇଟା ଓନ୍ଲି
ସେଇଟା
ଡେଟା
ପଚାରୁଛି।
ଫ୍ରେମ୍ ଇଏରେ ଯିବ ନା
ଆଚ୍ଛା।
କାହିଁକିନା ଆମେ ଏଠି ଡେଟା ଫ୍ରେମ୍ ଡଟ୍ ଏକ୍ସପ୍ଲେନ୍ କଲେ ତ ସେଥିପାଇଁ ସେଇଟା
ହୁଁ
ଡେଟା
ହୁଁ
ଫ୍ରେମ୍ର ଯେତିକି ରହୁଛି ସେତିକି ଯିବ
ଓହୋ ତ ଏଇଟା ଏଠି ହିଁ ଓନ୍ଲି ୱାର୍କ କରିବ ଡାଟା ଫ୍ରେମରେ ନା।
ୟେସ୍
ହୁଁ।
so now we can see inside the physical plan this is showing exchange round robin partition. Now let's understand this carefully. SPAC used round robin partitioning, meaning rows are distributed one by one. Let's see. Rows are distributed one by one. And something like, according to the round robin, it is something like row 1 is goes to the partition 0. Then row 2 goes to partition 1. Then row 3 goes to partition 2. Then row 4 goes to partition 3. Then row 5 goes to partition 4. And so on, like this. So now the question is how round robin partitioning actually assign rows to each partition internally. Means when we when it use the round robin partitioning internally, it first calculate total rows and according to that it will assign the rows into the partition. Means suppose there are 10 rows, and if we want 10 rows, and if we want 5 partition. So according to round robin partitioning, it will assign two rows, sorry, two rows to each partition. So in this flow, like row 5 goes to the partition 4, and then row 6 goes to the partition 5. Sorry, uh, 10 rows and 5 partition. So 2 rows per partition according to the round robin partition. So in this case, row 1 goes to partition 0, row 2 goes to partition 1, and in this way till row 5 it goes to the partition 4. Then again from row 6 it will start from again partition 0. This will go again row 7, partition 1. So then again we got 8 goes to partition 1, then row 9 goes to partition 3, then row 10 goes to partition 4. And in this way it will assign each row to the partitions. Means it will first calculate the total rows and total partition, how many we want the partition, and according to that it will assign the row to each partitions. So in our case there is 10 rows and 5 partition, so 2 rows per partition. So round robin partitioning provide 5 rows, sorry, 1 rows per partition, means 2 rows per partition. So row 1 and row 6 is inside partition 0. This is internally round robin partitioning happened. Now let's understand stage creation. This is very important. Before repartition, Spark was doing narrow transformation. So everything stayed inside same stage. But after repartition, this one, you can see the tag. Before repartition, Spark was doing narrow processing. So everything stayed inside same stage. But after repartition, shuffle started, and shuffle always creates new stage because Spark cannot continue processing immediately. First, it like shuffle write must complete, then shuffle data must be read again. Now Spark execution into multiple stages. So here we can see it is created 5 jobs. Now internally execution becomes something like it is in stage 1, it is read old partitions, then process rows, then shuffle write. Then after this stage happen stage boundary. Then in stage 2, shuffle read and create new partitions and process shuffle data. Now this happen in another stage. This is the process. This is actually internally happened. First in stage one, it read old partitions and process rows, then shuffle write. Then after that, the stage boundary happened and it will create another stage two. Then in stage two, it first shuffle read, then create new partition, then process shuffle data. In this is the actual distributed execution internally. Now let's connect it with task. Initially, we have 20 partitions. So initially we have 20 partitions. So Spark created 20 partitions. You see here. See, according to 20 partition, Spark will create 20 tasks. It has created 20 tasks. So in our Spark UI, it shows 20 tasks because one partition equal to one task. And after repetition, if you can see, after repetition, it only create 5 tasks because after repetition, there is 5 partitions. So Spark now created 5 tasks. That's why it is shows 5 by 5. Now let's understand shuffle right inside our SQL DAG. So here inside our SQL DAG, we saw like shuffle record written 10. In this section, it shows shuffle record written, meaning Spark wrote intermediate shuffle data. And this is temporary writing is called the shuffle write. Now, where this shuffle data is written, usually it written in memory first. Then, if memory is full, then it uh, write the shuffle data into disk. If memory is become full, if data is huge, first it write in the memory, then spill to disk. Like this. And this becomes this spill. This become the disk spill. Very important production concept. This is a production concept. Now, after shuffle write, new stage started. Now Spark must fetch shuffle data and read new partition data. And this become the shuffle read. So here, after shuffle write, it shows the record read 10. Means after shuffle write, it will read the shuffle. Sorry, after shuffle write, it read the shuffle data, which is same as 10. Meaning next stage has shuffle row here. Now the complete internal flow like in our case, initially it is 20 old partitions, then we create 20 tasks start, then rows read, then shuffle write, then exchange operator, then stage boundary, then shuffle read, then it create after the read create 5 new partitions. Created, then according to the task, it create 5 new tasks created, then final processing. So when we call repetition on a data frame, internally this flow is happen. First it read the 20 old partition, then create 20 tasks, then row read, then shuffle write, the exchange operator happen, exchange means shuffle happen, then stage boundary, then shuffle read, then 5 new partitions created, then according to that partition, 5 new tasks created, and then it processes the final processing. This is actually a repetition internal. Now let's understand a repetition by column. here we see like repartition by number. Just we pass a number, how many partitions we want. So according to that, it create that much number of partitions. So now let's see repartition by column. Till now we used like the df dot repartition and pass the type. Here's that only changed partition count. Rows were distributed randomly using round robin partition, discrete randomly. But now we are going to repartition based on a column. So for this, we can write, suppose we want a partition of department. So department df dot repartition to department. Now internally Spark behavior changed completely. Earlier, rows were distributed randomly in this path, but now Spark distribute rows based on department column. Now let's check the partition count first. Activity dot get number persons. So when we run this, see now it shows department partition is 3. From 20 partition, it now created 3 partitions. Now let's check the actual data. Partition data. Duties. This. See,
ଏମିତି ରିପାର୍ଟିସନ କଲେ ସେ ପାର୍ଟ ଫାଇଲ ମଧ୍ୟ ତିନିଟା ଏମିତି ହେଇ ରହିବ ନା ତିନିଟା ରିପାର୍ଟିସନ କଲେ
of course କାହିଁକି ନା ଏଠି ଯେତିକି ଆମେ ରିପାର୍ଟିସନ କରୁଛୁ ସେତିକିଟା ହିଁ ପାର୍ଟିସନ ଫାଇଲ ସେ କ୍ରିଏଟ ହବ ଇଣ୍ଟରନାଲ ନା ସେଥିପାଇଁ ଆମେ ରିପାର୍ଟିସନ କଲେ
Mhm.
so now it shows uh, three partitions file. Now look carefully. All IT department here, all the IT department is inside means all IT department rows came together and all HR department came together and all finance department came together like this. See. Now all the IT department rows came together and all HR rows came together and also all finance rows came together. This is not random anymore because initially we saw it is like provide the rows into the partition randomly. So now all we repartition on the department column. So it will according to that it will send the rows into that partition file means all the IT department into one partition, all the HR department into one partition like that. So now here is a question like how Spark decide this, and this is where the hash partitioning comes into picture. So here this is internally happened by using the hash partitioning. Initially we saw that has happened using the round robin partition, but now this has happened using the hash partition. Now let's see the actual physical plan here. Let's see if that will take it. See, now in physical plan, it shows the extensions happen using the hash partition. Initially, we saw the round robin partition, but now it is happened using the hash partition. So internally, it's something like using the hash partitioning, it is happened something like hash of IT, hash of IT, then hash of HR, then hash of finance. Internally, it happened like this. And then this all the hash value modulus into partition count. How many partition? One. Since our partition count is in our case the partition count is three because we passed the three as the partition. So in our case the partition count is three. Now according to that Spark internally does like modulus of 3, then modulus of 3, then modulus of 3. Internally happen like this. And based on the result, rows goes into partition because it will has then modulus by 3, uh, it will show a result, and according to that result, rows goes into partitions. Now, suppose internally it become IT goes to partition 0 internally according to the result. Then suppose HR goes to partition 1, then finance goes to partition 2. Internally, this has happened. Now all rows having same department value go to the same partitions. This is why output becomes partition 0 content here. Partition 0 contain the rows, all IT rows, and partition 1 contain the all HR rows, and partition 2 contain the all the finance rows. Now, this is very important in real-time project because many operations become faster if related rows stay together. For example, like when we call a group by or joins or aggregations or any window functions. So when we call internally, what happened in SQL, as we know, internally it will first combine all the department internally, then it calculate. So if we store the all the partitions like all IT department in one partition, all HR department in one partition. So internally, when we call a white transformation like group by join, then because of this, SPAC avoids unnecessary extra shuffle later. So we already combine all the same P data into one partition. So due to this, it will it will make the shuffle still make the shuffle, but less means the unnecessary extra shuffle avoids. Now remember something very important is even though we are repartitioning by column, SPAC still needs shuffle because rows must move between partitions. So suppose initially like Rahul, which is in IT department, is inside partition 1, and Priya is in IT department, which is all in partition 5, and Hiron, which is IT department, it is in partition 11. Suppose initially it is inside different partition. All IT department is initially inside presented inside different partition. Now after repartition by department, all IT rows must go into same partitions. Suppose it go into partition 0. So all the IT department must go into the same partitions. Internally, it happened like this. Now, SPAC must, in this whole process, SPAC must read rows, then remove rows, then regroup rows, then recreate partitions. In this whole process, internally, SPAC did this process. First it read the rows, then move rows, then regroup rows, then recreate partitions. But in this whole process, again, the shuffle is happens. So process the shuffle is happening. Now, if we see in the dash, on exchange, and let me call this department dot Now in stage one, it is read the read the partitions, then exchange happen, then shuffle alert, then in stage two, now shuffle data gets read again. Internally, execution becomes something like this. Old partitions, then task read rows, then shuffle write, then exchange, then stage boundary, then shuffle read, then hash partitioning applied, and it will create the three new partitions files. And this is actual internal flow. Now, this very one of in this case, there is one very dangerous production problem is DataSkew. This is one of the biggest Spark performance problem.
କଣ ଭାଇ ଡାଟା
DataSkew.
ସ୍କ୍ୟୁ
Skew. Yes.
ମାନେ ଗୋଟେ ପାର୍ଟିସନ ରେ ଅଧିକ ଡାଟା ପଳା ଆସେ ଆଉ ଗୋଟେରେ କମ ପଳା ଆସେ
ହଁ,
ସେଇଟା
ଯୋଉଟା କି unevenly ସେଟା partition ହେଇଥିବ।
ଡିଷ୍ଟ୍ରିବ୍ୟୁଟ ହେଇଯିବ ଅଲଗା
ତ ସେଇଟା ଦେଖିବା ହେଲା। Yes. For this, let's take another episode. Let's see. Suppose we take that now here when we create the data frame from this data. Now look carefully. Distribution is not balanced because here IT has 7 rows, HR has 1 rows, and finance has 2 rows. Now, when we create the data frame, first let's see the data. Okay, now it is 7 rows of IT department, 1 rows of HR department, and 2 rows of finance department. Now, on this, when we apply the repartition, like skew data repartition, skew here top repartition G on department. Suppose we want repartition on department. One,
ଅନଇଭେନଲି ଡିଷ୍ଟ୍ରିବ୍ୟୁଟ ହେଇଯିବ ନାଇଁ ସାତଟା ଗୋଟେ ଦିଟା
here the IT department goes into we did the repartition on department column. So all IT department goes into one partition, all HR department goes into one partition, and all finance into one partition. But look carefully, the partition distribution become uneven, and this is called the data skew.
DataSkewness.
skew. Now, because in our case, this is small size of data because there are only 7 rows. But suppose in production, partition 0 content 500 of GB data, and partition 1 contains 2 GB of data, and partition 2 content 5 GB of data. So now in production, what happens? One executor becomes overloaded because, as we know, one partition create one task in one executor. So one executor which can get the partition 0 data, which is the 500 of GB data. Now that executor become overloaded, and that executor works for very long time and consume huge memory. Also, sometimes if the data size is too large, then it spill data to disk, and also slow down entire stage. Meanwhile, other executions finish
Distributive
quickly.
processing ର ବି କିଛି value ରହିଲାନି ଏଠି ଆଉ।
ବାସ୍ ସେଇଟା ସେ distribute processing ହଉଥିଲା ଯଦି
ହୁଁ
ତିନିଟା
ହୁଁ
ଟାସ୍କ ରନ୍ ହଉଛି ତ ଅଲରେଡି ଦିଟା ଟାସ୍କ ସରି ଯାଇଥିବ ବଟ୍ ଆଉ ଗୋଟେ ଚାଲିଥିବ।
ହୁଁ ସେଇ
ତ
ଯାକ
ସେଇ
ଆହୁରି ଇଏ ଥିବ ଖାଲିରେ ଆଇଡିଆଲ ଥିବେ।
ବାସ୍ ତ ସେଇଟା ୱେଷ୍ଟ ହେଲା ନା, କ୍ଲଷ୍ଟର ରିସୋର୍ସ ଗେଟ୍ ୱେଷ୍ଟେଡ୍।
ହୁଁ।
Now, Spark job completion depends on slowest task also. Even if 19 tasks finished, but one skewed task still running, whole stage waits. So skew causes slow jobs and memory pressure and huge are called village executor imbalance, and this still also sometimes executor failure. So when data skew happen, it causes slow jobs and also memory, it will pressure the memory and huge shuffle delay, also executor imbalance, and sometimes if the data size is too large, then it will spill the data into disk. And also due to this, sometimes executor failure happen. Now let's see this in DAG. Maybe around this. This one. Let's see this. Here, see the duration. For task 1, the duration is 7 milliseconds, and task 2 is task 0, it is 7 millisecond, and task 1, 4 millisecond, and task 2, it is 4 millisecond. Now imagine in real time, there is 500 GB of data or 1 TB of data. So what will be the duration? But if our priority is like the whole pipeline is completed under 2 hours, so this will become the huge, and it will still running that. So this is the data skew. Now after shuffle, but in this case, still the shuffle is happening. See, because shuffle is still happened, but after shuffle, partition size become uneven. So internally, one task processed huge partition, as you see here. One task process huge partitions. So other tasks processed tiny partition. These two one tiny partition, and that become the skewed execution. Now connect this with executor and cores. Suppose cluster has 20 core availables, and if partition are balanced, 20 tasks, all cores are busy, perfectly parallelism. But in skew case, one huge partition and 19 tiny partitions. Now 19 tasks finished quickly, and one task runs for very long time, meaning only one core remains active, and remaining 19 cores are idle. That this is why skew is extremely dangerous in production Spark system. Now, the final understanding is repartition by number. It uses the round robin partitioning, and repartition by column use the suspension. And both purpose are like for round robin, but using round robin partitioning, the purpose is balance partitions evenly. And using the hash partitioning, the purpose is keep similar keys together. Now, this happen actually internally.
ରାଉଣ୍ଡ ରବିନ୍ ପାର୍ଟିସନିଂ ଆଉ ହାଉସ୍ ପାର୍ଟିସନିଂ ଏଇଟା ଆମର ସ୍ପାର୍କ ମାନେ ନିଜେ ତାର ଅପ୍ଟିମାଇଜ କରେ ନା
ହଁ ଏଇଟା ଇଣ୍ଟରନାଲି ସେ
ଇଣ୍ଟରନାଲ।
ପ୍ରୋସେସ କରେ, ଏଇଟା ଆମକୁ କିଛି କରିବାକୁ ପଡିବ। And these both repetition by number or repetition by column, this both cause the shuffle, exchange operator, and stage recreation, shuffle right, shuffle read, and white transformation. This both causes this. This is the total repetition. Now let's understand one more thing for this. Understand for this. Till now, everything we learned about repartition was heavily connected to shuffle, data movement, exchange operator, stage recreation, because repartition physically redistributes rows. But now, coalesce works differently internally. And this is one of the most important optimization concept in Spark. Now, first see uh, what is the main purpose of coalesce. usually coalesce is used when we want to reduce partitions, avoid unnecessary shuffle,
आई
reduce
ହେଇଗଲା
small files. Huh?
unnecessary आई ହେଇଗଲା यो
Oh, sorry. Unnecessary shuffle, reduce small files, and optimize final output writing. So when we want reduce partition size, partition number, and avoid unnecessary shuffle, and also want to reduce small files and optimize final output writing. So in those cases, we use the coalesce, and especially it is used before write a person. For write operation, we use basically coalesce. Now, suppose currently data frame has 20 partition. Here, suppose let's take this data frame. Let's take this data frame again. From this, it will shows the 20 partition initially. But if we use the coalesce on this, it will be equal to divide the coalesce 5. We did using the repartition previously. Now let's do it using the coalesce. Now when I run this, see, initial partition count 20, and after coalesce it is 5 because we passed the 5 coalesce. Now coalesce and we usually think like coalesce and repartition are same, but no, internally both work very differently. Now let's understand the difference. The create repartition creates full shuffle, meaning all rows can move anywhere. But coalesce avoid full shuffle, and the meaning is Hello, ମୋ voice ଆସୁଛି ତ?
ହୁଁ।
କରେଣ୍ଟ ରହିଲା ତ କଟିଗଲା। Okay, now repetition perform the full shuffle and all rows can move anywhere, but coalesce avoid full shuffle and it in this it will merge nearby partitions without complete redistribution. So this is the actual difference between repartition and coalesce. Now understand this carefully. Suppose initially we have partition 0, partition 1 and partition 2, like that, total partition 19, total 20 partition. Now we create df.coalesce. Now Spark tries something like new partition 0 merge old partitions and new partition 1 merge old partition, and same thing, new partition 2 merge old partitions, meaning SPAC mostly combines partitions instead of redistributing all rows. Now, this is the key reason coalesce is usually narrow transformation, because data movement is minimal. Now, let's compare this, like repartition happened, old partition 1 rows can move to partition 0, partition 2 and partition 4. So this happened in repartition, and that's why it is wide transformation, because it has many to many dependency. Repartition, but in coalesce old partition 1 mostly merge directly and very limited dependency. That's why it is a narrow transformation. This repartition rows can move to anywhere, like to partition 0 or partition 2 or partition 4. So this is many to many. So repartition is a wide transformation. But in coalesce, old partition 1 merge directly into another partition, and there is very limited dependency. So coalesce is a narrow transformation. Now, very important thing is, because coalesce avoid full shuffle, now what happened? Because avoids full shuffle. Now, what happened? Performance becomes faster and less network movement and also less shuffle right and also less shuffle width and also fewer stages because of coalesce avoid full shuffle. It impact on the performance and also less network movement and less shuffle read and write, and also it creates the fewer stages because in white transformation it creates so many stages according to the actions. Now understand one most important thing carefully. Coalesce is mainly good for decreasing partitions. For example, we did like from 20 partitions to 5 partitions. This is good. But suppose we try coalesce like df dot coalesce 50, means suppose we try to uh, create 20 partition to 50 partition. Now Spark cannot properly redistribute data because coalesce avoid full shuffle, because coalesce is mainly designed for the reducing partitions, not increasing. In our case, if we try initially in our data frame already had 20 partitions, then we write like df dot coalesce 50. Now Spark internal thinks coalesce is a narrow transformation and I should avoid shuffle. So Spark says I cannot create new data movement properly. They, so that because of that partition count remain 20. If we run this call increasing df, suppose we did like df dot coalesce 50. See, initially it is 20, and then we did like coalesce 5 from 20 to 5, then it converted, create 5 partitions. But when we want to coalesce 50, then it shows the 20 partitions because partition is basically designed for the decrease partitions. Sorry, coalesce is designed for the decrease the partitions. So increasing partitions using coalesce is not good. That is why a repetition is preferred for increasing partitions. Now let's understand the tag behavior. Where is the cheating?
Hello.
Oh, hello. Current खाली बारंबार जाଉଛି। See, initially in repetition, we saw in that like whole stage code gen. After that, it shows a exchange, but now it shows a coalesce. And in coalesce, there is nothing happened. Just it merged up all the partitions.
भाई आवाज कटुची स्क्रीन भी देखाउनी भाई
देखो
विश्व दुसुची स्क्रीन
Nine.
हाँ
Hello.
हेलो
Hello.
प्रभु भाई हेलो
हेलो
शुभुची
हेलो
Hello.
ଏବେ ଶୁଭାଯାଉଛି କି?
ସ୍କ୍ରିନ୍ ଦୁଷୁ ନଥିଲା ଆବାଜ ହେଲେ ପୁରା କଟି 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 ଶୁଭୁଥିଲା
Afternoon.
ଏବେ ଆବାଜ
କିଛି
ଆସୁଛି? ହ୍ୟାଲୋ
Hello.
କଣ ନେଟୱାର୍କ ଇସୁ କି ହ୍ୟାଲୋ ହ୍ୟାଲୋ ହଁ ଆବାଜ କିଛି ଶୁଭା ଯାଉନି ସ୍କ୍ରିନ୍ ମଧ୍ୟ ଦୁଷୁ ନଥିଲା ତମେ କଟି ଯାଇଥିଲ ତାପରେ କଟୁଛ ଆସୁଛ
Okay.
ହ୍ୟାଲୋ ଏବେ ଶୁଭାଯାଉଛି? ହ୍ୟାଲୋ ହ୍ୟାଲୋ
ଭାଇ କଲେଜ ଟା ପଢିଦେଲା ପରେ ଟିକେ ରଖିଦେବେ
ହଁ ହଁ
ଟିକେ
କଲେଜ
ଯିବାର ଥିଲା
ପରେ
ତ
ଠିକ ଅଛି
ହଁ ହଁ
କଲେଜଟା
ହୁଁ
ହିଁ ଲାଷ୍ଟ ତାପରେ କାଲି ଏଗ୍ରିଗେସନ ଦେଖିଦେବା
ଠିକ ଅଛି
okay now in repartition in DAG we saw like there is exchange but in coalesce there is no exchange only coalesce and in exchange there are so many things like the shuffle read shuffle write so many things happens but in coalesce it just merge the data. Now, repetitions creates new stage because shuffle exists, but coalesced avoid new shuffle stage and avoid exchange boundary and keeps execution lighter. Now, let's understand tax behavior. Suppose initially we have the 20 partitions. After coalesce, it is created 5 partitions. Now, Spark create only 5 tasks. See, 1 and 4, total 5 tasks. Same as repetition from outside, but internally much less movement happened. That is the difference between coalesce and repetition. Now let's see a time real time problem. Suppose in company we have a 2 TB of data, and after transformation it will create suppose 5,000 partitions. Transformation this created 5,000 partitions. Now if we directly call df 5,000 just a minute. Here, suppose if we directly call like df dot write dot perfect, something like that, then it will create 5,000 small files, and this become small file problem. This become and this is very common production issue. Too many small file causes slow file listing and also slow metadata operations, storage inefficiency, and also it slow down the query. So before writing, we use the coalesce. Like if we use like df dot coalesce 100. Now this 500 partitions will create only 100 small files, 100 partitions, meaning fewer output files, and optimized storage and better performance. And because coalesce avoid heavy shuffle, this become much cheaper than the repartitions. Now, one most important production concept is suppose partitions are already heavily skewed, badly unbalanced. Then coalesce may not fix that it properly because coalesce mostly merge partitions. It does not fully rebalance data, so skew may still remain. For example, like in partition 0, there is 500 GB of data, and in partition 1, there is 2 GB of data, 5 GB of data. In partition 2, there is 5 GB of data. Now, coalesce may simply merge partitions, but huge partition still remain huge. So, skew problem remains happens. In those cases, repartitions work better because repartition perform full redistribution and proper balancing and complete shuffling. Now, final most important comparison is repartitions. If we compare, this is the last one. Just
କୋଉଟା କେତେବେଳେ ଭାଇ ୟୁଜ କରିବେ ତ?
so look at this. Repartition the coalesce. And so we compare this. Okay. In repartition, we perform the full shuffle and wide transformation and exchange operator. Heavy network movement and proper distribution, and this is good for increasing partitions. So when we want to increase partition, then we use the repartition, and also good for the balancing data and then expensive. This is the expensive operation. So we basically, when we want to increase the partitions and balance the data, we use the repartition. But in coalesce, it is minimal shuffle and usually this is narrow transformation and less movement, and also it is faster, and this is good for decreasing partitions. So when we want to decrease the partition number, then we will use the coalesce, and also it is good for write operations, and also this is cheaper operation and but this may not fix the skew problem. So these are the comparison. So basically, when we want to increase the partition or balance the data, in that case we use the repartition, and when you want to decrease the partitions or write the data, in that case we use the coalesce. So repartition means old partition, full shuffle, then exchange, then new partitions, and in coalesce, old partitions merge nearby partition, and it is reduced partitions, much lighter internally. So this is the repartition and coalesce difference. That's it. Okay, କାଲି ଦେଖିଦବା aggregation ଆଉ window function ଟା
Okay ଭାଇ।
ଦେଖିଦବ, ମୁଁ ଏଇଟା ପଠେଇ ଦଉଛି, କିଛି ଡାଉଟ୍ ଥିବ
ହୁଁ
ଯଦି
ହୁଁ ହୁଁ
ପଚାରିଦେବେ।
ଏ ଯୋଉ ଏଇଟା jpg ଫାଇଲ କି png ରେ ପଠେଇଲେ ହବ ପରା?
ହଁ ଏଇଟା PNG ହେଇଯିବ ଆରାମସେ, ତାକୁ ସେ
ହୁଁ
ଟିକେ ସାଇଜ କରିକି ପଠେଇ ଦଉଛି।
ଠିକ ଅଛି, ଥ୍ୟାଙ୍କ ୟୁ ଭାଇ, ବଢିଆ ଥିଲା ସେସନ, ବହୁତ ଡିପ୍ ପଢେଇଲେ।
ସେଇ ମାନେ ମୋର ଟିଚିଂ ଏକ୍ସପିରିଏନ୍ସ ନାହିଁ, ବଟ୍ କନସେପ୍ଟ ଜାଣିଛି,
ହୁଁ
ସେଇଟା ହିଁ ଗୋଟେ ଇସ୍ୟୁ ହଉଛି। ସେଥିରେ ହବ ଆଉ, ଠିକ ଅଛି।
Thank you.
Yeah, thank you.
ହୁଁ ହୁଁ।